So we'll call up Dr. Shintaro Sato from Fujitsu. And we just talked about software, and now he'll talk about hardware.
Okay, thank you for the introduction. I'm Shintaro Sato. I'm head of the quantum laboratory at Fujitsu. Yeah, let me explain the activities in quantum computing at Fujitsu. Actually, Fujitsu is a kind of computer company. We do a service using computer. Actually, we developed the first computer 1950s using mechanical relays. Since then we have been working on the HPC technology for years. We developed supercomputer K with RIKEN. This FX10 uses the same processor as supercomputer K. And we also developed the supercomputer Fugaku with RIKEN. Then this FX1000 uses same processor as Fugaku. And we keep developing HPC technologies, and we now developing the next generation processor Monaka, and also the following generation processor Monaka X. While we are doing that, actually the improvement in computing performance is actually slowing down because of the what we call end of Moore's law is approaching. So many people now develop the new architecture, which has a specialized, specialized for specific application, so that we can do a speed up. In the same context, we developed what we call digital annealer, which has the architecture specialized for the combinatorial optimization problem. But anyway, these technologies still use CMOS. So for the future, we decided to work on the new principal computing technology, quantum computing technologies. And then this slide explains our strategy for quantum computing. We basically try to cover all the technology layers from device level, platform, software application, but not along with the world-leading research institution like RIKEN and TU Delft and Osaka University. As you know, there are so many hardware technology, and we don't know the final solution yet. So we basically try to put emphasis on the software technologies, which may not depend on the hardware technologies. As for hardware technology, we look into the several different technologies, but our resources are limited. So now we focus on the superconducting qubit technology with RIKEN in Japan, and also the diamond spin qubit technology with TU Delft in Netherlands. And for us, the application is very important. So we started developing application with end users even before we developed the actual quantum computer, using quantum computer simulator developed using our HPC technologies. Okay. Then as for the superconducting qubit technology, we developed the 64-qubit system about 2 years ago. And this April, we developed the 250-qubit system. We have a kind of scalable qubit design, qubit chip design. All the interconnect is from the back. So we can scale up without changing the design. So we can just tiling the basic unit, but we can scale up the qubit chips. But anyway, as for the 250-qubit system, we have to put every component, every part in the same width as the 64 qubits. So it's a kind of, there are a lot of integration issues. So we are, by doing an engineering effort, we are able to develop this kind of large-scale quantum computers. And then using this technology, we developed first commercial quantum computer for us, and which was delivered to the GQuad AIST in Japan this March. And this is the professor, Prime Minister Ishiba. I believe he's still Prime Minister, but anyway. Then we try to sell this kind of prototype quantum computer to the overseas right now. Then we are now developing 1,000 qubit quantum computer. Actually, the fridge for 1,000 qubit system is so big, so we actually decided to build a new facility to house this kind of large-scale quantum computers. So now it's under construction, then which will be completed by the end of this month. So after that, we can start building the 1,000 qubit quantum computers. Okay, we hope that we can launch the 1,000 qubit system next year, hopefully. And then last month we issued the new roadmap about the superconducting qubit technology. We aim to develop the quantum computer with more than 10,000 physical qubit, and also the aim to realize 250 logical qubit by the year of 2030. And as I explained later, we also aim to realize practical quantum computing by using our newly developed star architecture. It's a kind of new architecture using error correction technologies. And then, as I said, we also developed the quantum computer simulator, probably which is probably the world's largest class quantum computer simulator as a dedicated system. Now we can simulate up to 40 qubit using our system. And then using this simulator, we do a collaboration with the end user like Fizfilm, Mifo Financial Technology, and other material companies. And last 2 years, we also did a quantum simulator challenge. We let the users use our quantum computer simulator for free to develop the applications. Okay, it's a kind of contest. And then because our users want to simulate the larger number of qubits, we also try to develop the new type simulation software. We actually developing tensor network simulator with the Barcelona Supercomputing Center and decision diagram simulator with the University of Tokyo. Now our decision diagram simulator is on our platform. Now our user can simulate up to like 60 or 70 qubit for these specific applications. And then when we released the 64-qubit quantum computer, at the same time we released what we call hybrid quantum computing platform. Our user can use either the quantum computer or quantum computer simulator just by changing one line. Okay, so anyway, we can compare the result of the quantum computer to the simulator, and also we also developed the algorithm which both use the quantum computer and simulator, depending on the problems. And then now we keep developing this platform software. So now with Osaka University. So this spring we released such a platform software as OSS. So we'd like to develop this platform software together with the researchers all over the world. Okay, because it's very difficult for us to develop the really good software for ourselves. So anyway, we want to work with the researcher in the world. And then as I said, application is very important, and we work on of course, the quantum chemistry simulation and the finance application. But recently, we found a new application in robotics. Actually, this under the research collaboration with the Shintaro Institute of Technology and the Waseda University in Japan. Actually, the posture control of robot is very difficult in general. If you put your robot finger at this position, you have to adjust each joint, angle of each joint. So we assign each qubit to express the motion of the joint. Then it works, and we found that we can more efficiently control the robot posture using this quantum algorithm. So anyway, it's a still small scale simulation, but in the future we really want to apply this technique to the larger scale robotic system, so that we can find more application in this area. Okay, the details are written in this paper. Okay, and then for us error correction technology is very important. In the future, we really want to realize Fortran quantum computing. But it is said that we would need like 1 million, 10 million qubit to realize FTQC. So now we have only 100 qubit, around 100 qubits. So the question is whether we can do something with like a 10,000 or 100,000 qubit. So to do that, we actually developed a new architecture we call star architecture. Actually, the reason we need a lot of qubit is from two reasons. One reason is, of course, to make a logical qubit. And also, we really have to, after making a logical qubit, we have to do a logical gate operation. Okay, gate operation between logical qubit. But to do that, we also need unsealed qubit and extra gate operation. That's another reason that we would need such a large number of qubits. So we decided to, then the reason for needing such a large number of qubits is the implementation of the logical T-gate. T-gate is really costly. You need a lot of unsealed qubit and a lot of gate operation. So what we developed with Osaka University is we proposed a new gate set. We decided to forget about logical T-gate. Instead, we introduced the arbitrary rotation gate formed from actual physical gate rotation. So the point is, this phase rotation gate has errors. But it's kind of trade-off. By adapting this new phase rotation gate, we can reduce the resource of the logical gate operation. Like according to our estimation, we can reduce the number of qubits by 1/10 and number of gate operation by 1/20. So that's what we did. And then it was 2 years ago. And last year, we even improved that architecture. Basically, we improved the error rate of this phase rotation gate using some trick, okay? So we actually demonstrate that we can achieve the quantum advantage for practical application by just using 60,000 qubits. Okay, details written in this paper is really complicated story, but anyway. So we still try to improve this star architecture so that we can realize practical quantum computing with a smaller number of qubits. Okay. Finally, let me a little bit explain about the diamond qubit technologies. We basically try to, in this technology, we basically try to use electron spin formed at the defect in diamond as qubit. Okay. Typical example of defect is nitrogen vacancy center. And also we try to use the nuclear spins around it as the qubit. Then we consider this as a quantum module, okay? This as a quantum module. Then good thing about this technology is it can be operated at relatively low temperature, relatively high temperature compared to the superconducting qubit technology. It can be operated at around 1K to K3K, okay? Then also we can transfer the quantum information of this electron spin using photons. So we can scale up by connecting these quantum modules by photonic interconnect. So we thought that it's easier to scale up using this technology. But anyway, compared to superconducting qubit technology, it's not mature enough yet. So anyway, we are working closely with the TU Delft to develop this technology. And another important thing about this technology is we try to integrate everything into one chip. That means not only the qubit layer, but also the optical circuit layer and the cryo-CMOS layer. So it's a really challenging target. And the recent topic about this technology is beginning of this year, we actually demonstrated the high fidelity quantum gate operation in these technologies. We actually realized 2 qubit gate fidelity higher than 99.9%. It was estimated by the gate set tomography, very precise method. And also we realized the 1 qubit fidelity for nuclear spin with a fidelity higher than 99.999%. So it has a really good gate fidelity. Okay, so we are now trying to develop the prototype of this computer so that our user can use this prototype system through our platform. Okay. This is concrete remarks. As I explained, we are pushing the boundaries of both hardware and software to realize practical quantum computing as soon as possible. And we welcome new collaboration with the research institutions and companies to achieve this goal. Thank you for your attention.